Hello and welcome back to our journey through the solar system. Now, I mentioned last time that I might skip Earth, but I decided not to because how can you skip Earth? That's like the best planet, in my own humble opinion. Now, the reason that I was thinking about skipping Earth is because Earth has its own entire field of science and is it even part of astronomy? I don't know. That was kind of my thought process, but like I said, I think it's the best planet. It has got some really awesome, unique features, and I've been comparing a lot of the other bodies in the solar system to Earth, so it makes sense that I should talk about this wonderful planet that we live on. So unlike the other planets, Earth is actually not named after a god or a goddess. But because, we live on Earth, it actually comes from an Old English word, which I don't know how to pronounce because I don't speak Old English. But basically, this kind of word came into the language to mean the soil, the ground, the earth, the planet. So that's kind of the etymology of Earth. And then the personification of Earth in the ancient Roman and Greek pantheons is the goddess Terra or Gaia, also sometimes pronounced Gaia. So, though you might not guess it to look at her, Earth is actually 4.54 billion years old, give or take about 50 million years. Now, how do we know that? It's actually a little bit more complicated than you might think. So we can do things like date rocks on the surface of the Earth, but the surface of the Earth isn't constant over time. Thanks to our lovely plate tectonics, it's actually constantly reforming itself, and the surface of the Earth is younger than the entire Earth as a whole. The oldest rocks that we've actually been able to find are in Canada, and they're about 4.03 billion years old. We've actually found minerals that are even older than that, about 4.3 billion years old in Australia. Okay, so tectonics is kind of limiting us here on Earth, but the moon is basically forming at the same time as the Earth, and it doesn't have tectonics. So when we went to the moon, we collected some samples that we could use for dating, and that gave us a better idea of the, actual age of the Earth. And these moon rocks have been dated to be as old as about 4.5 billion years. Similarly, we can also use meteorites that fall to Earth and date those, and those are kind of some of the building blocks of the terrestrial planets way back when. And we find that those are about 4.53 to 4.58 billion years old. So we've narrowed in that the Earth is probably about 4.54 billion years old, which doesn't look a day over 60 billion. Now, one thing that is really exciting about Earth, and I don't know if you know this, but Earth is the only planet, the only body we have ever known of that can harbor life in the entire universe. We're kind of special like that. Now, we don't know exactly how long ago life formed on Earth. Researchers have made arguments for fossils that they have found that they think could be from microbial life for as far back as 3 to 4 billion years. In fact, one team recently proposed that these really cool looking tube things in this hematite rock were actually sheltering microbial life, and these are about 4.29 billion years old. But anyway you slice it, life has been on Earth for a very long time. Of course, we're talking about microbial life here, not life like you and me. We've only been here for the blink of an eye, cosmologically and geologically speaking. So this is kind of a rough timeline of the history of life on Earth. And so it goes back billions of years, but kind of the interesting life, depending on what your area of interest is, but for us, is very recent. Okay, let's talk a few physical facts about Earth. So I often reference Earth mass for other planets in the system, but what is an Earth mass? Well, it's almost 6 times 10 to the 24 kilogram, which is a lot, but also not a lot because Earth isn't that big in the grand scheme of things. Its radius is about 6,371 kilometers. Now that's an average because the Earth is spinning, and so that actually causes it to deform slightly, and so that the equator is slightly larger than the radius at the poles. And that's a difference of about 21 kilometers between the pole and the equator. The Earth has an axial tilt of about 23.5 degrees, so this is the tilt of the spin axis relative to the plane of orbit. And this is actually really important because this is what gives us seasons, which I can appreciate right now because we're coming into my favorite one, which is summer, but I was not so keen on this in the winter, cursing the axial tilt that gave us those long cold nights in Chicago. The mean surface temperature on Earth is about 287 Kelvin, which is about 57 degrees Fahrenheit, so that's actually pretty good. We can have water, we can have people. We like that temperature. And the surface pressure is a little over 100 kilopascals, or 1 atmosphere, or 1 bar. Or, there are many units that we could use, but that is generally an atmosphere of pressure. The Earth's orbital period around the sun is 365.25-ish days, and that 0.25 is actually why we have leap years, so cool. The solar day is 24 hours, as you might guess, and the sidereal day, which is basically the Earth's rotation relative to distant stars rather than relative to the sun, is actually about 4 minutes shorter. So of those 6 yada kilograms, that's 10 to the 24, what is all that material that's making up Earth? Well, the biggest component of Earth is actually iron, which is about 32% of the Earth. However, because iron is heavy, it sinks, and so most of that iron is actually found in the core. The crust, where we live, is dominated by silica and various forms of silicate. So this is what makes up the rocks and everything that gives us our nice continents and land and everything like that. And of course, between the crust and the core, you have the mantle, which is kind of this liquid magma ocean on which the plates are kind of floating around. We're getting into geology here, so I'm going to kind of brush by that, but it's pretty interesting. The Earth also contains a lot of water, and this is kind of a key factor of what we think is important for life here on Earth. And actually, the water is about 0.02% by weight. Okay, that doesn't sound like a lot, but I swear it is. In fact, if we had more water than that, it might actually be problematic because we wouldn't have continents, and it's a whole thing. So sitting on top of all this iron and silicate and water, there's a nice thin little atmosphere that the Earth has. It doesn't seem that thin when we're standing on it, but if you take a step back and look at the scale of the Earth compared to the atmosphere, you'll see the atmosphere is very thin. And this atmosphere composition has actually been greatly affected by the presence of life here on Earth. And no, I'm not talking about CO2, man-made CO2, although that is important, but I mean the presence of oxygen. So the reason that we actually have oxygen on Earth is from life. This was not what the prehistoric, not even prehistoric, this was not what the ancient Earth atmosphere was like. But thanks to all that evolutionary history of the past, billions of years, nowadays dry air is about 78% nitrogen, 21% oxygen, about 1% argon, and then, trace other gases, including carbon dioxide, which is up to about 400 parts per million in the atmosphere, which is about 0.04%. Now, I mentioned that we use moon rocks to help us date the Earth, so let's talk about the moon, shall we? Earth actually has a relatively large moon compared to some, in this big scheme of things. And the leading theory for how the moon formed was actually a giant impact back during the planetary formation stage with a protoplanet called Theia. And basically this impacted with the proto-Earth and then created kind of this ball of material that coalesced separately from the Earth but locked to it orbitally. Now the moon is tidally locked to the Earth in a 1-to-1 spin-orbit coupling. So this means for every one time the Earth rotates, it orbits once around the Earth. And this is the reason that the same side of the moon is basically always facing us and why we have the so-called dark side of the moon. Now the dark side of the moon is not actually dark, it receives just as much sunlight as the other side, but it is dark in the sense that we cannot see it from Earth. Well, most of it. We actually see a little bit more than half of the moon because it changes slightly, but that's not important. So we basically are always seeing the same face of the moon because of this tidal locking. And the moon is pretty neat, not just to look at, although it is. I highly recommend it. Even just a pair of binoculars, you can see some really cool things on the moon. But the moon actually stabilizes the Earth's obliquity. So this is that axial tilt that I was talking about. And planets can kind of have rapid changes in this axial tilt, but the moon stabilizes us against that. And obliquity can have a large effect on climate, which makes sense because I said that's why we have seasons, right? So the obliquity is obviously changing something about climate here on Earth. So the moon might actually be an important factor in how the Earth is so habitable. The moon also raises these tides on Earth. So basically the difference in gravity between the side of the Earth that's close to the moon and far from the moon leads to this deformation. And we see it mostly in the water, although the land also deforms slightly, but that's why we get high tide and low tide, because there's this bulge, this tidal bulge that travels around with the moon, and when the, kind of bulgy part of it is there, you get a high tide, and then when the not bulging part of it is there, you get a low tide. That was not a good explanation, but that's the basic idea. And actually, also because of these tides, it kind of creates this friction, right? Because the Earth is resisting this motion that the moon is inferring on it, or that the moon is pulling on it. And so it actually is slowly causing the Earth's rotation to slow down and the moon to get farther away as the energy and momentum is conserved. But not on any sort of time scale that, that we're going to notice. Interestingly, the moon at its current location is actually just at the right position far enough away from us to be the same angular size in the sky as the sun. Even though the sun is obviously much, much bigger, it's farther away, and those two factors basically offset almost equally. And so that is why we can have these really cool eclipses, these solar eclipses that we get here on Earth, because of this kind of coincidental arrangement of the moon and the sun, which is really neat. I don't know if you've ever seen a solar eclipse. I was really lucky to see one back in 2017, and it was really amazing. Pretty glad we have the moon for that. And in addition to this very large, wonderful natural moon that we have, Earth also has many, many artificial satellites. As of January 1st, 2021, there are actually 3,372 operational satellites around the Earth and over 20,000 pieces of space debris that are large enough to be tracked. It's a lot of little moons, a lot of little artificial moons. The largest of these is the International Space Station. So this has been just a very brief introduction to our wonderful, lovely home planet of Earth from sort of an astronomical perspective in the solar system. I hope you enjoyed it, and I hope you will come back next time when we talk about Mars. Thanks so much for watching. I hope you have a good one. Bye.